A matrix is essentially just a collection of values arranged in rows and columns. For example, we might have the four values 1, -3, 2, and -1 arranged in 2 rows and 2 columns. To signify that this is a matrix, we can use either square brackets or we can use round brackets, ordinary parentheses. Whichever convention we decide to use, we should stick to it. I tend to use this convention here, which is also most widely used in computing. Other types of brackets are not allowed. For example, these curly brackets called braces. Also, if you do use the square brackets, you do need to make sure you include these top and bottom parts of the bracket. If you miss them off so that it looks like this, then the result isn't a matrix, and in fact this expression has a special meaning which we'll see later. Matrices don't need to have the same number of rows and columns. For example, we can have the matrix 1, 2, 3, 4, 5, 6, which has 2 rows and 3 columns. This is referred to as the order of a matrix. So this matrix is order 2 by 3 because it has 2 rows and 3 columns. The number of rows is always given first. So this matrix up here is a 2 by 2 matrix, and because it has the same number of rows and columns, we say that this is a square matrix. The order of a matrix is also sometimes called the dimensions or the size. Matrices are usually given uppercase variable names. For example, I might call this one A and I might call this one M. A special case is where matrices are used to represent vectors. For example, V equals 1, 2, 3. If you haven't studied vectors yet, don't worry about this notation too much, except to say that a vector has 1 row or 1 column. Vectors are normally denoted by lowercase letters underlined or by bold letters. An important point to notice is that the elements in matrices are not separated with commas. This is incorrect notation again. Individual items from a matrix are called elements, so this is the element in matrix A in the first row and first column. We often want to refer to specific elements from a matrix, and we can do that by using subscript notation. For example, A, I, J means the element in matrix A in the ith row and the jth column. So this 3 here in matrix M, for example, is M 1, 3, because it's in the first row and the third column. If there are only a small number of rows and columns, you don't need to include the comma, so we can just put M1, 3, for example. The transpose of a matrix is obtained by swapping the rows and columns. For example, for this matrix A here, A transpose is a 2 by 2 matrix. It had 2 rows and 2 columns to begin with, so if we swap the rows and columns it will still be 2 by 2. The first row goes into the first column, and the second row goes into the second column. We can also transpose vectors, so V transpose, for example, will be this array here, and B transpose will be this array here. Notice the notation that I'm using for a transposed matrix, which is a superscript T. Another form of notation that is also accepted for the transpose is a prime, like this. Again, I tend to use the T notation here because the prime can sometimes be ambiguous in some contexts. Let's just write down the transpose of M as well before moving on. Since M was a 2 by 3 matrix, M transpose is going to be a 3 by 2 matrix. The first row goes into the first column, and the second row goes into the second column. In general, for a matrix M, we have the result that M transpose ij, so that's the element in the ith row and jth column of M transpose, is the same as mji. Let's try to understand that result. It says that the element in the ith row of matrix M transpose comes from the ith column of matrix M. And it says that the element in the jth column of matrix M transpose comes from the jth row of matrix M. Let's just practice a simple example question. Let's consider a 3 by 3 matrix with these elements in the first row, these elements in the second row, and these elements in the third row. Don't forget the square brackets to indicate that it's a matrix. I'll call it X, and then let's ask ourselves, what is the element given by X transpose 2, 3? So that's the element in the second row and the third column of X transpose. Well, since X transpose is given by swapping the rows and columns of X, the element in the second row and third column of X transpose will be given by the element in the third row and second column of X. So it's this value here. So the answer is -4. Okay, we'll now have a look at some basic matrix algebra. We'll start with multiplication by a scalar. And I'll start with an example. Let's suppose that we have the matrix X equals 2, 1, 0, -1, 3, 3. And suppose that we want to multiply it by 2 to get the matrix 2x. All that we do is we multiply every element in matrix X by the scalar. So we have 2 by 2, 1 by 2, 0 by 2, -1 by 2, 3 by 2, and 3 by 2. In general, if we take a matrix X and multiply it by a scalar, lambda, then the elements in the matrix are simply given by the scalar times the elements in the original matrix. Now let's look at addition of two matrices. The word matrices is the plural of matrix. Don't start calling a single matrix a matrice, which is something that I commonly hear, which is incorrect. As well as our matrix X, let's define another matrix Y, which will make equal to -1, 0, 2, 1, 1, 2. To add together matrices X and Y, we simply add the corresponding elements. So X plus Y is equal to 2 plus -1, 1 plus 0, 0 plus 2, minus 1 plus 1, 3 plus 1, and 3 plus 2. So we get the result 1, 1, 2, 0, 4, 5. So the element in the ith row and jth column of the result is given by the element in the ith row jth column of x plus the element in the ith row jth column of y. Here x was a 3 by 2 matrix because it has 3 rows and 2 columns, and y was a 3 by 2 matrix. In order to add two matrices together, the number of rows and columns in each must be the same. That is to say, the order must agree. So if I was to define another matrix, M equals 1, 2, 2, 1, then I wouldn't be able to add this matrix to either x or y. An important case where this comes up is if we try to add a scalar to a matrix. So suppose we wanted to add 2 to every element in x. This expression here is incorrect. The number 2 is basically a 1 by 1 array, and we can't add arrays if the order doesn't agree. So if we want to add 2 to every element in x, then we need to define a 3 by 2 array where every element is 2. So we've looked at addition of two matrices, and we've looked at multiplication by a scalar. We can combine these two steps to get a linear operation on two matrices. So for example, we might have minus 4 times x plus 2 times y. So we have minus 4 lots of 2, 1, 0, minus 1, 3, 3, and 2 lots of minus 1, 0, 2, 1, 1, 2. And the results are given here. For example, for this element in the second row and third column, we have minus 4 times minus 1 plus 2 times 1. In the next video, we'll take a look at matrix multiplication, which is quite a big topic by itself. But before we do, have a go at the examples here to make sure that you fully understand addition and multiplication by a scalar. Solutions are given in the accompanying notes.